Okay, thank you. So thanks for inviting me to this exciting meeting and giving me the opportunity to present our work, especially because sort of the main direction of our work is slightly different from lots of other speakers at this conference. So it's a good opportunity to talk about our results, which are more in the sort of more conventional condensed matter direction, where we're interested in the electronic transport in various conventional as well as novel materials, and try to see whether hydrodynamic approach can help us understand what's going on in actual experiments. So I'll start by very sort of one slide reminder of the electronic transport itself. So usually that's simply how one studies electronic properties of solids experimentally. So traditionally, you assume that sort of linear response of the electronic system towards external bias, and the external bias can be either electric field, either electric field or a temperature gradient. Then one can measure either electric current or the heat current. And then the coefficients that you can see here, this is a standard linear response coefficients, the electrical conductivity, thermal conductivity, and the thermoelectric power. Now, if we are talking about non-interacting system, so free electrons scatter off some sort of disorder, then the standard textbook results are shown here. They have a Joule formula for the electrical conductivity. Thermal conductivity is sort of proportional to electrical conductivity, such that the ratio of the two, this so-called Lorentz number, is some sort of a constant. Right? Now, at the same time, if you apply magnetic field, then there will be classical Hall effect, with the corresponding Hall coefficient being an important measure of carrier density. And that, in fact, is used by most experiments in order to characterize their samples, in order to actually measure what is the density of charge carriers in their system. Now, in traditional materials, for example, in copper, these predictions work reasonably well, even if not exactly perfect, right? So here, for example, here I have a standard plot from some engineering textbook of the Lorentz number in copper. And you see that at very low temperatures, this universal value is more or less obeyed. At a very high temperatures, this is more or less restored. And then in some intermediate temperature, depending on how pure copper is, there is some violation of this Wiedemann-Franz law, but violation is not very strong, right? Maybe in a factor of 2 or 3, right? Now, if you look at the temperature dependence of the resistivity in copper, then again, from some engineering textbook, you see about 3 distinct regimes. And so at the very lowest temperatures, you have a constant temperature independent resistivity, which is typically attributed to disorder. Then there is some intermediate regime where there is a fifth power of the temperature, which is typically attributed to electron phonon scattering. And then once the Debye temperature is exceeded, then the resistivity becomes linear in temperature. And that's where phonons sort of play a role of static disorder, right? So the specific values of the resistivity, they strongly depend on how the material is prepared, whether it's annealed, whether there are some impurities, whether it's alloyed with some other materials. But in all of these, even though the actual value of the resistivity may vary quite strongly, the temperature dependence remains sort of linear, because this mechanism of the phonons playing the role of static disorder is sort of remains valid. Now, in other systems, for example, in 2-dimensional electron systems and heterostructures, the main focus is on something else, because the copper, even though it's we look at very wide range of temperatures, in all of these range of temperatures, copper more or less, or electronic system in copper rather, more or less remains to be a Fermi liquid, right? Or at least we can try to describe it from the Fermi liquid viewpoint, and that's all justified by the fact that the Fermi temperature is very, very large. Whereas in semiconductors, Fermi temperatures can be fairly low. And then in these systems, one can study different aspects of electronic behavior. So for example, one question is this so-called metal insulated transition that's shown here on the left. And that's where, so different curves correspond to different carrier densities. And then different carrier densities correspond to different strengths of electron-electron interaction. And that now is the first example where interaction becomes important. One way of trying to understand these curves is to look at the quantum interference corrections to the semi-classical Drude-like picture, and that's where interaction plays a role and may distinguish between metallic-like and insulating-like temperature dependence. However, completely, this behavior here is not very well understood. And even less well understood is behavior on the right, where there is this profound minimum in temperature dependence of resistivity at temperatures which already exceed the Fermi temperature. Now the electronic system is not degenerate, and then the behavior of interacting system, which is not degenerate, is even harder to describe than the one in the Fermi liquid sort of regime. Now, interactions are typically very difficult to describe in many body systems. So if we have a weakly interacting system, then we can use some sort of perturbation theory. If by some miracle the system behaves as a Fermi liquid, then this sort of Fermi liquid theory takes care of the interactions by itself, even though still the particles are still interacting there. Or in one-dimensional systems, again, by another miracle, it may happen that systems are integrable, and then we have other mathematical techniques to deal with that. But in a majority of real materials, interactions are hard to deal with. And then when you talk about systems such as strongly correlated systems, heavy fermion compounds, great superconductors, and so on and so forth, there very often a proper theoretical description is lacking. And therefore, it could be that the idea of hydrodynamics is attractive, because hydrodynamics describes sort of transferred behavior of a strongly interacting system, even if we don't quite understand the microscopics of that system very well. So water is, of course, the prime example. Hydrodynamics originated as a description of water flow in canals and so on. But microscopics of water is very, very complicated, whereas hydrodynamic equations that govern the flow of water are sort of simpler. And so there could be a hope that hydrodynamics may equally help us to understand observable behavior of electronic systems. Now, as a sort of an example of traditional hydrodynamic behavior of a conventional fluid, let's recall the so-called Poiseuille flow, which is a flow of viscous fluid through a pipe or between parallel plates, or if we are in a two-dimensional settings, then in sort of channel-like geometry. So for a flow in a pipe, that's a textbook problem, which tells us that if we assume the so-called no-slip boundary conditions, saying that the viscous fluid is basically stationary at the edges of the pipe, then The velocity has this typical parabolic profile with the velocity maximum in the middle of the pipe. Then the throughput of the fluid is proportional to the force power of the radius. And that's basically extremely important in even such a remote, I mean, for physicists, remote, but practically extremely important application as hematology, where that basically explains to you how the width of a blood vessel is extremely important for your health. If you're changing a little bit, then your blood pressure changes dramatically. Whereas another feature of this viscous flow is that if we are, for example, as in this picture, this circles or white, this gray or white obstacles here, they're just obstacles for the fluid randomly placed in this channel. And what the fluid wants to do is to flow around those obstacles rather than scatter off them. And in that case, it might actually be more effective in transporting the fluid through the system than sort of a ballistic flow where particles scatter off everything. And in particular, this type of behavior is key to understand the so-called superballistic transport experiments, which were performed in graphene a couple of years ago. Now, I just said that it could be extremely attractive to talk about hydrodynamics for electronic systems, but this is rarely done, or at least until recently, it was very rarely done. It was once proposed by Radi Guruji in Soviet Union many years ago, that if you have a very clean, very narrow sample, then you may observe a transition from this free particle Knudsen flow to the sort of viscous Poiseuille flow by changing temperature in your system. And that basically is based on the fact that the electron-electron scattering lens that describes interactions and that describes so whether viscous behavior is formed or not, that length scale is temperature dependent, whereas the width of the sample is not. And so at the very lowest temperatures, the resistance is determined by scattering of the edges, and therefore is temperature independence. But then this interaction length scale kicks in, the viscous behavior is formed, and then the resistance goes down, right? Because the this viscous fluid, as I showed before, is more effective in transporting carriers or charge in that matter than ballistic system. And then, of course, eventually phonons will take over, and the resistance will grow. And so there is this profound minimum predicted by Guruji that is supposed to be the hallmark of this viscous flow in electronic systems. Now, that effect has actually never been observed in experiment, although in '95 there was an attempt of observing the Guruji effect in gallium arsenide heterostructures. There, instead of looking at temperature dependence of resistivity, people looked at the non-monotonic behavior of the differential conductance and argued that this specific double peak profile is sort of equivalent to the this temperature dependence minimum observation, right? However, after '95, there was a long pause in experimental studies of electronic hydrodynamics, which was only revived sort of 5 or 6 years ago with the graphene and the onset of sort of ultra-high pure materials. And the reason for this is very simple to understand. Water molecules, they sort of exist in space where we assume all kinds of conservation laws about them, whereas electrons exist in a solid and may scatter by crystal lattice, right? They scatter of all kinds of impurities or more generally lattice imperfections. And they also scatter on phonons, which are lattice vibrations. And normally these two mechanisms dominate the whole temperature range accessible in experiment, and then there is no room for hydrodynamics, which would require the electron-electron interactions to be the dominant scattering mechanism, such that the electron-electron time scale would be much shorter than any other scale in the system, including impurity scattering, phonon scattering, or any other scattering mechanism you can imagine. And because of the different temperature dependence of those, that relegates hydrodynamics to an intermediate temperature window. And so this inequality is not really an inequality, because it's not like there is a special temperature associated with disorder, a special temperature associated with phonons, but it's just simply to indicate that at the very low temperatures, typically disorder scattering dominates. At higher temperatures, typically phonon scattering dominates. And so hydrodynamic behavior is possible if there exists an intermediate temperature range where electron-electron interactions dominate. And then weak disorder or weak electron phonon scattering can be considered as sort of weak perturbations on the sort of background of the formed hydrodynamic behavior. Such temperature windows is not necessarily guaranteed to exist in any given material. And in fact, in most practical materials, it probably doesn't exist. However, there are now several examples of these so-called ultra-pure materials where this behavior does seem to exist experimentally. At least there are many experiments where some hints or evidence for this behavior has been observed. And then also theoretically, we can consider a limit where electron-electron interaction is in fact the dominant mechanism, and then we can establish what would be the consequences of such regime for observable quantity. Now, graphene is the material where the this hydrodynamic behavior is mostly studied experimentally, and I think also theoretically. Experimentally, because obviously that's the material where which can be made very, very pure, and where lots of aspects are very easily controlled, or I mean, easily from a theorist viewpoint. Experimentally, it might actually be very difficult. But and then also more recently, several techniques were established for imaging electron flow. So instead of measuring some global quantity such as resistance, one can now observe, so to speak, the current density profiles, which is to some extent similar to observing the water flow. When we observe water flow, we can simply look at it. We cannot simply look at electrons, but these imaging techniques may help to sort of bridge that gap, right? And so graphene, because of it's two-dimensional and not necessarily inside a heterostructure, it's sort of a perfect material to apply this imaging technique. Now, the electronic hydrodynamics in graphene we call unconventional because the conservation laws that that are observed there are slightly different than in conventional fluids. So first of all, the excitation spectrum of quasi-particles in graphene is linear, and therefore there is no Boolean invariance in the system, and as such we cannot simply copy the standard dynamic equations and apply them to electrons in graphene. Even though the spectrum is linear, there is also no true Lorentz invariance, because Lorentz invariance would then require that Coulomb interaction would in fact be a two-dimensional and then relativistic, which doesn't really happen in graphene. The electrons interact with just a regular three-dimensional Coulomb interaction, which is also not in any relativistic limit. So again, because there is no Lorentz invariance, we cannot simply copy relativistic hydrodynamic equations, and therefore these dynamics in graphene has to be sort of developed from scratch, so to speak, on its own. And there is another very important point, that due to the linearity of the spectrum, the momentum density in graphene is proportional to the energy current, right? And that means that the hydrodynamic flow in graphene is actually energy flow. It's not mass flow as in water, and it's not charge flow as Guruji was mentioning it for regular electronic systems. Here it's an energy flow. Now, if we are in a strongly doped regime where graphene is very similar to a regular thermoliquid, then all kinds of flows, energy flow, particle flow, charge flow, they're all basically the same. And then there one can use more traditional theory, whereas close to the charge neutrality, that's the point where the fact that there are two bands of carriers, graphene, that becomes very important. And the fact that the dynamic flow is in fact the energy flow, that becomes very important. And that's where the resulting behavior is quite different than what we expect in a conventional fluid. So the fact that there are two bands leads to a second. So normally dynamics reflects three conservation laws: particle number, energy, and momentum. Now, if we have two bands, we may think that in some limit, particle number in each band independently is conserved. That gives us an extra conservation law and an extra macroscopic current. But this conservation law is approximate because, of course, there are these so-called recombination processes, most notably super collisions, which is a collision of an electron with a phonon and impurity, right? But then the impurity allows not to conserve momentum, and the phonon takes away the energy. This way, the electron and holes can sort of recombine. And the same mechanism may also contribute to weak violation of energy conservation. And in fact, because we are in a solid, there is also disorder scattering. Therefore, weak disorder scattering cannot be completely neglected. Therefore, momentum is also weakly not. So, if the however, when we assume that the electron-electron scattering dominates, then all these decay processes that are shown here in red, this sort of weak, and one can still consider that mostly electrons behave hydrodynamically, but these decay processes also have to be taken into account. Now, lastly, using green terms, they're basically coupling to electric and magnetic fields, which also don't happen in water, right? Water molecules are neutral; they don't couple to electromagnetic fields easily, but electrons obviously do, and so that has to be taken into account. Now, once we convert these continuity equation for momentum density in sort of the Euler equation, then in graphene we will get this generalized equation where this black terms, that's a standard Euler equation, the green terms, that's coupling to electromagnetic fields, this red is the weak decay during disorder, and then this blue term is the one sort of remnant of relativistic theory, right? So these Dirac fermions, they want to be relativistic, they have the linear spectrum, but everything else is not, and so the system is not really relativistic, but there is one remnant of that, and that's this time derivative of pressure here is in this equation. Now, when we look at the static properties, such as regular electric resistance, this time derivative then plays no role. And so just to identify that in the degenerate limit, namely strongly doped graphene, this equation clearly recovers the standard linear response theory, right? You can just consider a bulk or infinite system where none of these gradients are important, and then this dual heat term is beyond linear response, you neglect that as well. And so all that remains is the regular Drude-like or Ohm-like transport equation that produces the standard Drude-like resistivity and then the regular type of a Hall coefficient. However, if you are in at the Dirac point or close to the Dirac point, then it is important that charge and energy decouple. And then there are two bands that are responsible for this. And that's where Hall coefficient vanishes due to the particle-Hall symmetry at the Dirac point, and then magnetoresistance is parabolic. But that magnetoresistance is really proportional to this disordered scattering time, and that tells us that there are some quantities where this disordered scattering cannot really be neglected completely. Now, another such quantity is obviously the thermal conductivity, because, as I said, this momentum density in the system is proportional to energy current, and if I neglect disordered scattering, then momentum is conserved. That's why there is no mechanism to relax the energy current, and therefore there is no thermal conductivity. Rather, it's infinite.
Sorry, can I just ask a question?
Yeah.
Yeah. So just to make sure, I mean, in when you write the hydrodynamic equations, can you go back one more slide? Yeah. So the fields that you consider are there the electron numbers in the two bands N and Ni.
Yes.
And then the energy density.
Oh, no. So N and I, they're linear combinations of those, right? So you have a conduction band and valence band.
Yeah.
Right. The difference in densities gives you sort of the charge density.
Okay.
And then the charge is obviously conserved. So then you have a real continuity equation. And then if you add those two densities, then you get this Ni, what's sometimes called imbalance density. Or rather, you can say it's a total number of quasi-particles in the system. And that is important, especially at the Dirac point, because if you are specifically at the Dirac point in graphene, then this N here, it's simply zero, right? That the natural graphene is neutral, right? The charge density is zero. However, if the temperature is not zero, then you have some temperature-populated electrons and holes in these conduction and valence bands, and overall there is a density of those quasi-particles that is proportional to temperature. That's why you have these two. Separate continuity-like equations. One of them is a real continuity equation because of charge conservation, and the other is approximate because there is this weak decay due to these quasi-particles recombining. Right. Then, additionally, you obviously have energy conservation, right? So then this left-hand side, that would be sort of the continuity equation for the energy density and energy current. But now, because the electrons are charged, you have Joule heating, and that's this term here. And then you also have weak violation of energy conservation because of those super collisions, or practically electron phonons scatter, right? Where your electrons, they scatter on the phonon, and then this phonon simply takes the energy away from the electronic system and never comes back, right? Now, the same thing with momentum. Now, phonon scattering does not violate momentum conservation, but disorder scattering does, right? So if you have disorder in your system, then momentum can be lost in the process of electron impurity scatterings, and therefore this also has to be included. And then, of course, momentum density is also affected by electric field and magnetic field. That basically is the Lorentz force, right? Acts on those electrons. Right? Now, normally in a regular classical hydrodynamics, you look at this momentum density continuity equation, this one here, and then you rewrite it as the Euler equation, right? So these terms here in black, they're completely equivalent to these terms in black. That's sort of your textbook standard hydrodynamics, right? Now here, because there are additional terms, there's something that's related to the electromagnetic fields and to disordered scattering, they appear here as well. And then these two terms, so that one comes from the heat, and this term comes from the sort of relativistic nature of electrons, or sort of nearly relativistic nature of these Dirac fermions, and that's part of this stress tensor that you have to write down explicitly in terms of the velocity in order to derive the Euler equation. Right?
Okay, and what's the K subscript in the for the momentum field? There's a K subscript in the.
K is a momentum. N, it's just that N, I use N for density, so K is momentum, so N sub K is a momentum density.
Can I also ask a question?
Yeah.
So in usual hydrodynamics, you have sort of three equations. One is continuity equation, another, but okay, there are three equations, like Euler equations downstairs, and the third one is, you know, energy or entropy equation.
Yes.
And so here, if you have somehow three different fluids, if you wish, N, Ni, and Ne, it seems that you have like a lot of Euler equations, obviously. You have this index. Yeah, but,
no. Euler equation is only one, right? So so basically what you have here, the fact that you have two, that's because you have two bands of carriers, right? So even in the regular hydrodynamics, suppose you have a two-component fluid, right? Then depending on what kind of scattering between those two components you have, you may write continuity equation for one component and the continuity equation for another component, right? So you got to think of these two bands more or less as two components of this combined fluid, but we write the linear combination of those two components rather than simply electrons and holes, basically because there is this weak violation of each individual conservation laws for electrons and holes, whereas their difference, which just simply gives you the charge density, right? That's inviolable, right? That's our regular standard continuity equation, right? Now, then you have the conservation of energy and conservation of momentum. Conservation of momentum, you rewrite as an Euler equation. Now, the conservation of energy in standard hydrodynamics, in the ideal fluid, you simply leave it as the energy density or the energy continuity equation, or you may rewrite it as a continuity equation for entropy.
Right.
And then once you consider dissipation, so viscosity, thermoconductivity, and so on, then you typically expand this equation for the entropy, right? And then that becomes this thermal transport equation, right? So now here, sort of, I focused on this Euler equation because I wanted to point out the fact that this ideal hydrodynamics in graphene already has some experimentally observable consequences. But of course, the full set of hydrodynamic equations does include this thermal transport equation, which is basically equation of how entropy is affected by all these scattering processes. Now, coming back to thermal conductivity, we can use these dynamic equations to calculate the electric current and heat current and set it up in the form that is basically similar to the this traditional linear response theory. And then from here, you can read off microscopic expressions for the conductivity, electrical conductivity, and thermal conductivity. And then specifically at the Dirac point, the electrical conductivity is completely described by the electron-electron interaction. And then it has this sort of a universal value that is was obtained by a number of authors. That's why I apologize I didn't hide these papers here on the slide, but the slide is busy. It is. And then the thermal conductivity is directly proportional to the electron impurity scattering time, because, as I said, impurities, that's the only mechanism to relax the energy flow. And so the ratio of this of these two conductivities, the Lorentz number, is proportional to the ratio of the electron impurity scattering time and electron-electron scattering time. And by design, so to speak, by the assumption of the hydrodynamic region, this ratio is very, very large, right? And therefore, this Lorentz number exceeds the standard universal value that I talked about it before by a large number. So here, if I just put some values of parameters, I get number 50. And then in experiment, that's more like 20, but it's still a very, very big number, right? So here on the left is the experiment done in Harvard on the thermal conductivity of this Wiedemann-Franz law in graphene, where you can see that the this Lorentz number exceeds the standard free electron value by a factor as much as 20 in this intermediate regime, which is close to the Dirac point, so close to zero the charge density, and it's an intermediate range of temperatures, which is we've been talking about so far. Now, it turns out that outside of that region, so for example, at high densities, here and here, in doped graphene, you see this blue, it's not so easy to see on this curve, on this plot, but this deep blue here responds to zero. In fact, the Lorentz number in this sort of doped graphene is very, very small. So the Wiedemann-Franz law is violated there as well. And that smallness of Wiedemann-Franz law was seen also in topological materials, where this violation occurs at lower temperatures rather than reasonably high temperatures. And so it was conjectured that this violation of Wiedemann-Franz law in these topological materials is also a hallmark of some sort of hydrodynamic-like behavior in the systems. However, from a theoretical viewpoint, the systems are significantly less understood compared to graphene. That's why sort of more talking about graphene here. Now,
can I ask one question?
Yeah.
This constitutive relation that you had written, just the transparency before that. There was a constitutive relations you showed. This transport coefficient, how are they calculated? Just yes, this one. The J is
all right. So basically,
how are
okay. So so I didn't write the constitutive relations, right? So here I wrote for you the results, so to speak. So these hydrodynamic equations, right? On one hand, they can be written, or these continuity equations. On one hand, they can be written phenomenologically, basically saying that continuity equations simply reflect conservation laws, and therefore they can be just written phenomenologically, or they can be derived based on the kinetic theory, right? So the idea.
I'm not asking that. What I'm asking is that constitutive type relation that you close those equations. Yes, this proportionality constants. Where did you get it from? What sort of theory is used to?
That comes from the kinetic theory.
From kinetic theory.
Yes.
Theory of electrons. So are they considering only sort of uncorrelated motion of those electrons, or there are more effects accounted for? When these...
So basically, kinetic theory describes electron-electron scattering in the limit where one can still assume electrons to be independent quasi-particles, right? So therefore, the idea of this kinetic calculation is such that you start with whichever interacting Hamiltonian for quasi-particles in graphene, and then you use the renormalization group to go into the parameter regime where these particles, they're sort of weakly interacting, weakly not in the sense that the coupling constant necessarily is extra small, but the fact that they are still independent quasi-particles, and therefore the kinetic theory is applicable, right? Now, once the kinetic theory is applicable, you can also renormalize to the regime where the coupling constant is small enough such that the equation becomes actually solvable. Then you solve this equation, but then you renormalize back to the sort of experimentally relevant parameter regime, and then you basically you trust that these resulting hydrodynamic equations are universal enough so that this procedure is in fact valid. And that is very much similar to what happens in traditional hydrodynamics, where you may derive the regular Navier-Stokes equation by looking at the kinetic theory of a dilute gas. But then the same Navier-Stokes equation you use to describe water which is not a dilute gas, which is a strongly interacting system for which you do not have any microscopic theory at all, right? But nevertheless, you describe it by the same Navier-Stokes equation. Now, of course, in the Navier-Stokes equation,
you describe it by the same equation, but you have a different transport coefficient. So what I'm asking, when you calculate those transport coefficients, you use microscopic theories.
Yes.
And in this electronic system, you also use microscopic theories. Are those theories are only at the level of completely uncorrelated motion, or there are correlated motions taken into
I'm not entirely, but I don't know what you mean by correlated motion. What I'm telling you is that the microscopic theory that he used.
I mean going beyond Boltzmann level in kinetic theory language.
No, that's not beyond Boltzmann. That's the kinetic theory, right? Okay. These are calculated with the help of the kinetic theory. Now, then these results of the kinetic theory, they are adjusted with the help of the renormalization group, right? To renormalize from the regime where the Boltzmann theory is valid to the regime of the experimentally relevant parameter values, right? So this renormalization procedure sort of takes into account the fact that the interaction in sort of experimental graphene is actually strong and not weak, right? But at present, there is simply no other theoretical means to calculate these things, right? However, comparison with experiment, as I will also show you in a couple of later slides, is quite reasonable, right? So qualitatively, this combined sort of kinetic and renormalization group calculation, at least qualitatively, definitely accounts for what's seen in experiment, and then, you know, a more precise calculation is of course welcome, but at this time I don't think we actually have any reliable means of doing better analytical. Right? Good. So now,
thanks.
These conclusions so far, one could make them already at the level of ideal hydrodynamics. However, of course, the real hydrodynamic is not only ideal, right? You got to take into account dissipation. And now here, it's important to say that already at the level of the ideal theory, there are already some scattering processes that are yielding these conductivities or resistivities. And then in certain sense, dissipation is sort of already there. However, when we mean dissipative terms in hydrodynamics, we mean those terms that appear due to electron-electron interaction. So these would be viscosity, and in the conventional fluid, thermal conductivity, and in this electronic fluid, electrical conductivity, which at charge neutrality in graphene is only attributed to electron-electron scattering. Right? That means now that both electric and its imbalanced currents, they're not just proportional to the hydrodynamic velocity, but they acquire these dissipative corrections. And dissipative corrections, they are linear in the applied fields, whereas this sort of conductivity or quasi-conductivity matrix, that comes from a perturbative solution of the Boltzmann equation, similarly as it's done for thermal conductivity in the conventional hydrodynamics. Right? Now, this produces a certain number of scattering rate-like parameters that describe conductivity in graphene. And these parameters can be extracted experimentally, for example, by using optical conductivity. So in a recent experiment in Berkeley, people studied exactly the optical conductivity in graphene close to charge neutrality. And there they managed to discern different temperature dependence of the electron-electron scattering time, linear here, and the electron impurity scattering time, this curve here, right? Such that if you go away from the Dirac point, then the optical conductivity has two contributions. One is this kinetic contribution, and that's exactly corresponds to these corrections, delta yacht, this dissipative correction to the current. Plus, there is a hydrodynamic contribution, which is exactly this this density times velocity contribution to current. And so, because it's density, therefore the corresponding conductivity is proportional to density square, and at the Dirac point that's 0. So that's precisely at the Dirac point there is only this kinetic contribution to conductivity that's important. And so then these two different these two different scattering rates that appear in this expression, they actually can be extracted experimentally, right? Now, if you put together both of these contributions in the optical conductivity, then each of them individually look like these dotted lines in this picture, but overall you have this blue line, so it's a like Lorentzian-like curve that describes optical conductivity in graphene, which is more or less what's an experiment. Now, as a side remark, I want to point out that very similar assumptions of the optical conductivity were used in theoretical sort of conjectures about the behavior of the so-called bad metals, which is strongly correlated to electronic systems where individual quasi-particles don't practically exist, and therefore a standard kinetic approach is not valid anymore. And so there, in these systems, people used a combination of sort of phenomenology to various hydrodynamic conjectures in order to come up with this sort of optical conductivity type of behavior, which is, however, very, very similar to what you get in graphene by means of this kinetic hydrodynamic calculation. And so hopefully in the future, one can extend these approaches and then describe these so-called bad metals sort of in a better way, but also hydrodynamically. Now, once we start introducing dissipation, then of course we want to introduce viscosity. So viscosity is introduced here in exactly the same way as in conventional hydrodynamics. Namely, you take the stress tensor at the dissipative part, and this dissipative part you take as linear in the gradients of velocities, right? And so the specific form of this correction is governed by symmetry. And so in 2 dimensions, that's this combination of gradients that you have here, with eta being the shear viscosity and eta h being the Hall viscosity. In the absence of magnetic field, the Hall viscosity obviously is 0, and the shear viscosity at charge neutrality in the absence of magnetic field is also given by some universal-like expression, right? That can also be calculated in terms of this kinetic theory. And now this now is very helped by the fact that this product of a coupling constant and the velocity of the Dirac fermions, this product is actually not renormalized under this RG in graphene, and therefore this expression is expected to be valid at low enough temperatures. Now, another feature of this electronic system in graphene is that the bulk viscosity is practically 0, at least within the approximations that one uses in this kinetic theory. So similar to how bulk viscosity is vanishing in standard Fermi liquid hydrodynamics, but there it's approximate, right, to the measure of T square over the Fermi energy square. But on the other hand, in the ultra-relativistic hydrodynamics, it also vanishes. So therefore, at least it's not surprising that here in graphene, at least in some approximation, there is no bulk, right? Now, viscosity in graphene, at least in doped graphene, was measured in the measurements of non-local transport. and the values are shown here, so that the kinematic viscosity is more or less 0.1, depending on the temperature and density in your graphene. And so calculations based on the kinetic theory of this normalization group approach, they basically yield very similar results. A little bit, right? The values that we have here, the quantitative values are slightly larger. So instead of 0.1, we get something like 0.2, 0.3. So a little bit larger values, but qualitatively a very similar behavior. Now, unlike the experiments in doped graphene, one can also calculate what happens at the Dirac point with viscosity. And that was also recently addressed in imaging experiments. So now there are more than, but originally there were these two suggestions where when either images electronic flow in graphene with a nanotube SCT, or with using a sort of a magnetometer, and the role of the magnetometer is played by this NV centers and diamonds. So this experiment in Weizmann Institute or Weizmann-Manchester collaboration focused on exactly this Poisson flow in doped graphene, whereas the Harvard group was focusing on the Dirac point and trying to exhibit this Poisson flow of Dirac fermions. Right now, in doped graphene, the Poisson flow does sort of exist, except that it's not always a parabola. It's more like a catenary curve, but it's basically this type of curved flow that's seen in experiment, right? However, in order to derive this expression, one has to assume the so-called no-slip boundary conditions, right? That's what I mentioned before. These are the typical hydrodynamic boundary conditions that are assumed in conventional hydrodynamics, where people are saying that the viscous fluid is somehow, there's some sort of friction at the edge of your pipe or channel, such that the fluid constituents, which are located exactly at this edge, they don't move at all. And so there you have zero velocity at the edges. Now, in graphene, it's been calculated that, again, based on various kinetic approaches, that these no-slip boundary conditions are not really realistic. And in fact, experimentally, it's always also was established that the mixed boundary conditions with a finite slip length are more appropriate. And also here in this experiment, you can see that this current density doesn't really go all the way to zero. Even in this theoretical picture that's shown here, doesn't go all the way to zero at the edges of the channel, which is basically the effect of that slip length. Now, what's interesting about this experiment is that people compared hydrodynamic behavior with ballistic behavior, right? So what does that mean? If we look at this channel or strip of graphene and we think that it's narrow enough, then normally we have to compare the mean free pass of electrons to the width of the channel in order to establish whether diffusion is established or not, right? So normally for non-interacting electrons, you look at this disorder mean free pass and you compare the disorder mean free pass to the channel width, and by changing the channel width, you can observe the so-called ballistic to diffusive crossover, right? So that's something that I can show you here. So basically, if you have this geometry with the channel, right, then you have to, and then if you require this diffusive scattering of electrons at the boundary, then depending on how the width of the channel compares to the mean free pass, you either have this diffusive behavior, which is this blue curve here, which is practically flat in the bulk and only changes a little bit at the edges, or you have this sort of curved behavior in this ballistic regime, right, where electrons scatter only on the boundaries and not on any kind of impurities. And though that ballistic scattering is also, you see this profile is actually curved. And so that's what was pointed out in this experiment, that in the ballistic regime, right? So the ballistic regime, again, that's where the disorder mean free path is very small. However, the electron-electron interaction is not dominant. Now, this hydrodynamic regime, that would be where the disorder mean free path is small, but the electron-electron interaction is dominant, such that the corresponding length scale is even smaller, right? However, in both cases, the current density profile is curved. And now, within the experimental accuracy, it's very hard to distinguish between these types of curves. Therefore, in experiment, they have to look at the whole field, which remains flat even in the ballistic regime in non-interacting systems, and is curved in the hydrodynamic regime to distinguish the two cases. Right? Now, another experiment that sort of indicates the existence of viscous flow in graphene, or rather in electronic system, was done in an ultra-pure gallium arsenide system, where they deliberately made sort of a big macroscopic obstacle in this channel-like structure, and then they show that in the regime where they think electrons behave hydrodynamically, the flow in the case where the obstacle is, right? So then in the hydrodynamic regime, they flow way more effectively with the obstacle than in the ballistic regime. That's what something they implied at the very beginning of the talk. Okay, now let's move towards this viscous flow at charge neutrality. And that's where graphene is very different from the regular fluids, because here electric current is not hydrodynamic at all. You see, electric current has a hydrodynamic contribution and then this dissipative kinetic contribution, but hydrodynamic contribution is proportional to the charge density, which is 0 precisely at the Dirac point. Therefore, at the Dirac point, electric current is decoupled from the energy flow, that is the hydrodynamic flow in graphene. And this Navier-Stokes equation doesn't have any electric field anymore in it, and therefore this energy current cannot be driven by the electric field, at least in the absence of the magnetic field. And therefore, in the absence of the magnetic field, there is no Poisson flow that can be induced by the electric current. And then what you can have is you can apply magnetic field. And if you apply magnetic field, then some inhomogeneity of electric current will establish. But that inhomogeneity looks very different from the Poisson flow. You see, the Poisson flow, as we were talking about in this doped graphene, it looks like this. It has a very small velocity at the edge and maximum velocity in the middle of the channel. And now here, this inhomogeneous flow at the Dirac point looks opposite. The maximum velocity, or the maximum electric current rather, is at the edge, and the minimum is in the middle. That's why we call this picture anti-Poisson flow, right? Now, how am I doing on time?
You're into discussion time, but you have 10 minutes now.
Okay. So then I'll just point one more thing, and then I'll finish. So this type of behavior predicts that something happens at the edge of our channel much more than in the bulk. Right? Now, let me just skip slides here and show this experiment that was recently done at the Weizmann Institute. Here, they have a different type of imaging technique where they specifically focused on the edge current in the situation where graphene is subjected to the magnetic field, which is what I was talking about with this anti-Poisson flow. And this experiment shows that indeed, if graphene is subjected to the magnetic field, most of the current is flowing along the edges. However, this flow appears to be not hydrodynamic in a sense that if you put a tip from this scanning the scanning probe, right? If you put this tip at some point at the edge, as is done here in this picture, and apply extra potential so that you essentially block the electronic flow, the current is not going to behave hydrodynamically in a way that hydrodynamically you would expect that this current simply flows around this tip, such that this tip potential will simply redefine what exactly is the edge for this electronic system, but rather this current stops here and and goes off into the bulk. So this experiment shows that at the edge of graphene, there exists some other edge state, some sort of a classical, non-topological current carrying state that is different from any kind of bulk hydrodynamic mechanism. And therefore, that gives you sort of another puzzle that needs to be understood and sort of needs to be incorporated into this whole picture of dynamic behavior of electrons that otherwise seems to be is qualitatively quite consistently describing experiments in dynamic regime in graphene and others. But then, since my time's up, I'll just give you with a conclusion, and maybe there are some questions.
Thanks, Boris, for this really nice talk. Yeah, we can now have questions.
Yeah, for instance, one question is, and I perfectly understand that you have a really, really complicated system and you want to be close to what people measure, but somehow, for instance, you were talking that you were using Boltzmann, okay, maybe I didn't understand, but your electrons, Coulomb interaction, so it's long range, and we know in a simpler systems and plasmas, it's very, very difficult to apply Boltzmann directly to like plasma, and so people use sometimes sort of ignore collisions, but in a very smart way. So they write first Vlasov equation, and if they want to try to take into account collisions more like a little bit at least, because somehow it diverges if you do it, in a trivial way when interaction decays, like I guess faster than 1 over r to the power 2 in 3 dimensions. So one potential decays faster, should decay faster, so you can apply. So they use like Balescu, Landau, Leonard, few some important works in the like 50s and 60s, which sort of gave some, collision-like torn. And but can't you try to do similar?
So we sort of do, right? So this loss of cell consistency is definitely there. So we're definitely including this, and that is and that is sort of unavoidable, basically because in experiment you measure, or rather the voltmeter that you apply to your system, it measures the response not to the external electric field but rather to the total electric field. So which means you have to include the electric field that is induced by density fluctuations or by any density inhomogeneity that you have in your system, and that practically is the Vlasov term, right? Now, of course, in the traditional plasma physics, when you do collisionless hydrodynamics, you include the Vlasov terms, or rather the Maxwell equation, but you completely neglect the collision integral, right? Yes. Now, here we don't neglect the collision integral, but we are helped by the fact that due to this linear spectrum in graphene, the collision integral basically diverges for almost all modes in the kinetic equation, with the exception of 3, right? So you have momentum conservation, and then due to the momentum conservation, there is one mode that is sort of momentum-like mode that for which the collision integral simply vanishes, And then, if electrons in 2 dimensions with this linear spectrum, if they flow along the same direction, so if electrons are collinear, then if in the scattering processes all velocities are aligned, then again this this divergence doesn't exist, right? And so like this, there are 3 modes for which the collision interval doesn't diverge. And so then you can use this divergence in order to reduce your collision interval to this what we call 3-mode approximation. And then within this 3-mode approximation, you can completely solve the kinetic equation. And this way you can obtain all these microscopic expressions for viscosity, conductivity, and so on, right? Now, all of this you only need in order to obtain these microscopic expressions for the kinetic coefficient. You don't really need this in order to derive the general form of the hydrodynamic equations. And in that sense, it is similar to how it is in sort of water versus gas, right? I don't know of any theory, at least of any analytical theory, that can calculate viscosity of water, right? In a dilute gas, you could calculate the viscosity by solving the Boltzmann equation, but then that result has nothing to do with the viscosity in water, right? But the Navier-Stokes equation is the same, right? Now here, in graphene at least, it appears that your kinetic coefficient, your kinetic calculation for viscosity is not far off from what is measured experimentally, at least when you take into account this renormalization from the sort of weak coupling regime where kinetic theory is definitely valid to the regime of sort of experimentally relevant where the coupling is not small, right? So of course, if you have a free-standing graphene, then this coupling constant is basically 2, so it's not small. But even if you encapsulate graphene in some dielectric substrate, which is usually this hexagonal boron nitride, then because of this dielectric environment, this effectively the coupling constant goes down, but it's something like 0.2, 0.3, so it's not very small anyways, right? Therefore, you need to use this renormalization group in order to sort of renormalize your results in the weak coupling regime to this sort of experimentally relevant regime. And then, you know, that can be done sort of within the 1 loop RG as typical in condensed matter physics, but the results are very reasonable. So they are definitely of the same order of magnitude as what's measured in experiment, and the temperature dependence, at least qualitatively, is also seems to be correct. Therefore, just perhaps it so happened in graphene that these calculations are not far off. Right?
If no other questions, nobody asked. I ask second question. Sorry. So for instance, you described that you know that you have some like 3, not 4, different from ordinary case, like 4 transport coefficients. You know, Hall viscosity, like shear viscosity, bulk viscosity, and thermal conductivity, at least that I understand. But kind of, you know, maybe naive question, but, you know, for instance, I remember like in 2 fluid, like hydrodynamics, I don't know, like maybe helium 2 or something. So there were really like more, there were quite a few, and there were no Hall viscosity, but there were quite a few those kinetic transport coefficients. And very, very long time ago, I just browsed a little bit some book by Patterman, I forgot the name. So, and that guy was saying that actually, like in maybe the most famous book, Halatnikov, about this 2-fluid hydrodynamics, there were like 5 viscosity coefficients, but if you do really honest calculations using phenomenological, you know, all assumptions, you have like 13. You have a lot of, and why not in your case when you have somehow, at least visually, it looks like, you know, 2 fluid or whichever, you know, N and I, why don't you have, I don't know, great many. Of course, they're extremely difficult to measure. Even in ordinary fluid, for instance, bulk viscosity is very difficult to measure, you know. So So some of them may be relevant and practical, well, but
basically, this simply refers to the symmetry of the problem. So viscosity typically is defined as a sort of response of the stress to strain to stress response, right? So generally speaking, it's a force rank tensor, right? And this force rank tensor obviously can have a whole lot of components, right? Depending on the symmetry, if you assume rotational symmetry in your system, as is done usually in the conventional hydrodynamics, then this tensor that is your stress tensor here is then there's this one coefficient and it's proportional to this combination of these gradients of velocity, and this particular form is then due to rotational symmetry, such that this whole force rank tensor is reduced to a single coefficient, which is a shear viscosity.
That's all I understand. I guess maybe I was confused. Somehow I really thought that you have almost like two fluids, you know, almost because you have two different N and NI. So, but if you have just one velocity field, I understand what you mean. I understand. Yeah, that's of course, yes, obvious. Yeah. Okay.
Okay, so I think we have finished this. We've run out of time, and so we have to stop here. So thanks a lot, Boris, for this really very clear and beautiful talk. So we end this session here now, and